Curvilinear coordinate system 17. Consider a scalar function phi of position which depends on the cylindrical coordinates rho phi z such that phi is equal to rho cosine phi. So we have already done part B. We have calculated the gradient of this scalar function. We found the radial and azimuthal components. Now part A asks us to plot the surfaces of constant phi in the xy plane. I will do that in the end. Part C, the field lines for V can be described by a function rho of phi. Show that rho of phi satisfies the equation d rho of phi d phi is rho v rho divided by v phi, and solve the above equation for rho of phi and plot the field lines on the same graph you plotted the surfaces of constant phi. Okay, so in Cartesian coordinates, the field lines are given by dy dx is equal to vy over vx. And here we have the displacement vector dr is dx ex hat plus dy ey hat. Now if we do the same thing in cylindrical coordinates, in cylindrical coordinates, we're going to have the displacement vector dr is equal to del r del rho d rho plus del r del phi d phi plus del r del z dz. And what is del r del rho? It is h rho in e rho hat direction. So we have h rho d rho in e rho hat direction. Then we have h phi d phi in e phi hat direction. And then we have hz dz in ez hat direction. We've already calculated these scale factors. H rho was 1, so we have d rho e rho hat. H phi was equal to rho, so we have rho d phi in e phi hat. And then we have hc equal to 1, so we have dz ez hat. So now if we look at the ratio of the azimuthal component rho d phi to the radial component d rho, this must be equal to the azimuthal component of v divided by the radial component of v. So this means that if I take the reciprocal of this, and also note that this rho will go with v rho, I can write this as d rho d phi is equal to rho v rho divided by v phi. So you can see here rho is a function of phi. So that was what was suggested in part C. The field lines are described by this function rho of phi, and it satisfies this equation. Now part C says solve this equation and plot the field lines. So if I solve this equation, I can collect rows on one side, d rho over rho is v rho over v phi d phi, but v rho is cosine phi, v phi is minus sine phi. So substituting that here, I have integral d rho over rho is equal to minus the integral cosine phi divided by sine phi d phi. So let's double check this. We have d rho over rho, v rho over v phi, which is minus cosine phi over sine phi d phi, minus cosine phi over sine phi d phi. And in order to perform this integral, I'm going to call sine phi to be u, and in that case I will have cosine phi d phi is equal to du. So this will give me, the left hand side is integral d rho over rho, that gives me natural logarithm of rho, and the right hand side is minus du over u, so that's also equal to minus natural logarithm of u, and here I have a possible constant c, and this is the natural logarithm of 1 over u, because the minus implies this natural logarithm of u to the power minus 1. But u was sine phi, so I'm going to write this as natural logarithm of 1 over sine phi plus a possible constant c. So let's keep this as a constant c. And this gives me, if I take the exponential of both sides, this gives me rho of phi to be e to the c multiply e to the natural logarithm of 1 over sine phi, so it's 1 over sine phi, and that means I can write rho of phi as a constant c divided by sine phi. So c is a constant. All right, so we worked on this field lines. dy dx is equal to vy over vx when dr is written this way in Cartesian coordinates. But if we work in cylindrical coordinates, we have del r del rho d rho plus del r del phi d phi plus del r del z dz, which is h rho d rho e rho hat plus h phi d phi e phi hat plus h z dz ez hat. So substituting for h rho 1, h phi rho, and h z 1, we obtain this. And the ratio of the azimuthal part to radial part, rho d phi over d rho, is equal to v phi over v rho. That's analogous to this. So we obtain this equation for rho of phi. And we can solve this equation by collecting rho terms on one side and phi terms on the other side, where v rho is also a phi term, it's cosine phi. V phi is minus sine phi and multiplied by d phi, and then we integrate both sides, and this gives us rho of phi. By doing a sine phi equals to u substitution, I recognize this to be an integral of minus integral du over u. This is d rho over rho. So this is natural logarithm rho, and then I have minus natural logarithm u plus c, which means u to the power minus 1 inside the natural logarithm. So that's 1 over sine phi. So my answer for rho of phi is c divided by sine phi. So in the next video, we're going to plot the surfaces of constant phi and also plot the field lines on the same plot where we have shown the constant phi surfaces.